A particle starts from rest at O at time t equals 0. It travels along a straight line with acceleration 24t minus 16 meters per second squared, where t is the time measured from the instant when the particle is at O. Find its velocity and its distance from O at time t equals 3. Here we have an example of non-uniform acceleration. You can see that the acceleration depends on the time. It varies linearly with time actually. Like for example at time t equals 0, if we plug 0 into this thing here, we get 24 times 0 minus 16, we get minus 16 for the acceleration. So the acceleration is pointing to the left if we take directions to the right as positive. So the acceleration is minus 16 at t equals 0. What happens at say t equals 1? If we plug 1 in here, we get 24 minus 16. 24 minus 16 is plus 8. So at t equals 1, the acceleration is plus 8. So the acceleration is obviously varying with time. As a matter of fact, after t equals 1, the acceleration will keep on increasing in magnitude. So at t equals 2, the acceleration would be 24 times 2, or 48 minus 16. That's 32, so the acceleration will be much greater in magnitude at t equals 2. So we get the picture. The acceleration will increase with time. We know from previous videos that the acceleration at an instant, a at any particular time t, is the derivative of the speed with respect to time at that time t. Okay, now you know, in the past we have only dealt with constant acceleration, so it did not matter what the time was. You know, we could actually just get rid of the time. It made no difference. A was the same for all times. V, however, varied with time. But if we differentiated V with respect to time, we just got a constant regardless of what the time was. Here we have a different story. But the same ideas apply, of course, for getting the acceleration. To get the acceleration, we need a change in the velocity divided by the time taken. Except we're getting the instantaneous acceleration here. So you know, the changes are infinitesimal. It's dv, a tiny change in v, divided by the time taken, which is dt. These are infinitesimal quantities. So that'll give us the acceleration at that instant of time t. And you know, the acceleration will vary, of course, as I said. So here we have a formula for the acceleration. It's a of t is 24t minus 16. That's equal to dv dt. See, it's not a constant, it depends on time. So we have a separable differential equation here. We separate the variables, dv on one side, all the v's on one side, and t's on the other side. So we multiply 24t minus 16 by dt. And next we integrate both sides. So if we integrate dv, we get v. We can get the speed at any particular time. So we add 1 onto the power and divide by that power. So 24 divided by 2 is 12. 12t squared. Integrating minus 16 is it's a constant. We just multiply it by t. Now there are two ways we could do this problem. We can use indefinite integrals and put a constant here and solve for the constant. Okay, so this is the first way that I will do it. Next I will come back and use definite integrals. We'll put limits on these. But let's do it this way. How do we get c? Well, we have some information about the speed at a particular time. We know that the particle starts from rest. So when t is 0, u is 0. That's what we were given. Well, we won't call it u, we'll just call it v. We'll use v to stand for the speed at any time. So v at time 0 is 0, since the particle starts from rest. That's what's given in the question. So this is obviously a function of time. So we use the fact that v of 0 is 0. So we plug 0 in here. Well, that's just going to give us 0. We're going to get another 0 here. Okay, so this is the result of v of 0, and we know that it's equal to 0. So straight away we can see that c must be 0. So we found the constant of integration. That means we can write down a particular solution for the differential equation. V of t is 12t squared minus 16t plus c, which is 0. Alright, so now we found the speed at any time. So we can answer question 1. We want the speed at time t equals 3. I'm calling it the speed because, well, it's really the velocity. The speed could be negative actually. As a matter of fact, it will be in this situation. It'll be negative for some of the time. Okay, so I should really say the velocity, because if we were just talking about speed, the speed would be positive. Speed is the magnitude of a vector. It's always positive. Anyway, just plug in 3 for time. So we get 12 times 3 squared minus 16 times 3. This does come out to be positive. So at 3 seconds the particle is moving to the right. At 3 seconds the speed is 60 meters per second. A positive sign indicates that the velocity vector is pointing to the right. Yeah, so more accurately, v actually gives us the velocity. Like if you get v at time 1, for example, this is just on the side. If you plug 1 in for t, you get 12 minus 16, which is minus 4. The velocity is minus 4 meters per second, which means that at t equals 1 second, the direction of motion is to the left because of the minus sign. So the velocity vector points to the left and has magnitude 4. So the speed is actually 4. You know, if you wanted the speed, you could indicate it with these vertical lines. The speed at time 1 is 4 meters per second, but the velocity is minus 4 meters per second. The speed is the magnitude of a vector, always positive. Next we want the distance from O at time t equals 3. Oh sorry, one thing I forgot to do was to redo this problem using definite integrals. Okay, I just want to redo this. So if we go back to the question, we want the velocity and the distance from O at t equals 3. So we know something at t equals 0. So the particle starts out at t equals 0, and we know that the speed at that time is 0 because the particle starts from rest. We're interested in the speed, or sorry, the velocity at t equals 3. So we're looking for the velocity at t equals 3, okay? So we could have done it this way. If you integrate 1 with respect to v, you get v. As I said in a previous video, we should really call this v prime. We can't use the same symbol here for the differential as we do for the limit, because we're summing these differentials, whereas this v prime is meant to be a fixed quantity. Okay, so the v is variable, but the v prime is fixed. But you know, if you don't put v prime there, it doesn't really matter too much. We can be a bit loose with the notation once we know what we're doing. Okay, when we work this out, we plug in the upper limit v in for v, well that's v, then minus, and then plug in the lower limit 0, well that's just v. Plug 3 in, well we get the same thing as we got before, then plug 0 in, we'll just get 0, and you see we get the same answer as before. We find that v is plus 60 meters per second. Again, I just want to say that v is a vector, even though there's no arrow on it. For some reason in linear motion arrows are omitted, so we're dealing with a vector quantity here, so this could be positive or negative. It's not the speed. Normally we use the letter v for speed, so this is a little bit confusing. So because we're using the letter v for the velocity, which means it can be positive or negative, for the speed, which is just always positive, it's never negative, we'd have to use vertical lines on either side. Okay, now let's get the distance. Here's v of t. This was the particular solution to our differential equation when we integrated this thing, and well, we got a constant of integration, but we saw that since v of 0 is 0, the constant of integration c is 0. Alright, so it's important to get the particular solution, because we need to integrate v to get the distance. Okay, v is just ds dt where s is the distance. So we've got an easy differential equation to solve here. Separate the variables, integrate ds to get s. S is the distance of the particle from the origin at any time. S is some function of time, of course. So we're going to get t cubed here, and 12 divided by 3 is 4. We're going to get t squared, 16 divided by 2 is 8. And we have a constant of integration. How do we find c? Well, we use the fact that the distance of the particle from point O at t equals 0 is 0. So plug 0 in here. Well, that's going to give you a 0. You're going to get a 0. So s of 0 is c. And we know that s of 0 is 0. The distance of the particle from point O at time 0 is 0, because the particle is at point O at that time. So now we have our particular solution. We can see that c is equal to 0, so we can replace c up here with 0, which means we can get rid of it. So we found a particular solution to the differential equation, and now we can answer the question. We want the distance of the particle from the origin at t equals 3. Okay, plug in 3 and you get 36 meters. By the way, s is a vector. You don't see an arrow on it, but it's actually a vector. S can be positive or negative. We get a positive answer here. So the particle is at plus 36. S could be negative, you know. You can see if you plug in 1, for example, you get 4 minus 8, which is minus 4. At t equals 1, the particle is actually to the left of O. It's at minus 4 when t is 1, if you check that out. So since s can be positive or negative, it's a vector. If we are just interested in the distance of the particle from the origin, we have to consider the magnitude of s. Okay, that'll give us the distance, which is a positive quantity. So for example, if s comes out to be minus 4, then the distance from the origin is 4 units, or 4 meters. In the next part, we want the value of t when the speed of the particle is 80 meters per second. So what we do is we set the speed v of t equal to 80. So we get a quadratic equation in t. So we have to have 0 on one side. Okay, you can divide this by 4, and it has factors. Set each factor equal to 0, the usual, and you get t equals 10 over 3. When you set this first factor equal to 0, the other solution is minus 2. But the timer starts at 0, so we disregard a negative value for t. So the answer is 10 over 3 seconds. A particle travelling in a straight line has a deceleration of v squared over 400 plus 16 meters per second squared, where v is its speed at any time t. If its initial speed is 40 meters per second, find the distance travelled before it comes to rest. Now, the deceleration is actually a magnitude. It's the magnitude of a negative acceleration. So, this particle has negative acceleration. Acceleration is a vector, even though for linear motion we leave off the arrow. It has two directions, it can be positive or negative. Since this quantity is the magnitude of a vector, the deceleration is the magnitude of a vector, it's always positive. And you can see that that's the case. V squared is always positive. Well, v is the speed is always positive, but if you square a quantity, you always get a positive result. We divide by plus 400 and add on 16. So clearly this quantity here is always positive. Well, it has to be, because it's the magnitude of something. It's actually the magnitude of a vector that is pointing in the negative direction. Okay, so there's only two directions, positive or negative. So now we can write down what the acceleration is. Well, we take the magnitude and stick a minus sign in front of it. So we want the acceleration to be negative if the particle is to decelerate. So if we have a positive quantity and stick a minus sign in front of it, we get a negative quantity. Okay, let's look at a picture. At t equals 0, the particle is here. Its acceleration vector is pointing to the left, that's the negative direction. So again, we take directions to the right as positive as we usually do. The acceleration vector is always going to be pointing to the left. No matter what the speed v is, this quantity is always going to be negative. Okay, if we minus a quantity that's always positive, we get a quantity that's always negative. Now we know the particle is going to come to rest, so the particle must be moving in to the right. It can't be moving in the same direction as the acceleration vector. It can't be moving this way, because if it's moving in the same direction as the acceleration vector, then the particle is going to speed up actually, and it's never going to come to rest if that's the situation. So we need to know that the particle is going to come to rest in order to know that the direction of the velocity is to the right. You know, it's possible that the direction of the velocity could be to the left. We still have a deceleration. Even though the particle could be moving to the left and speeding up, we could call that a deceleration. You know, it's a particle with negative acceleration. It's just moving in the wrong direction, but speeding up. So a particle with negative acceleration could be either moving to the right and slowing down, or it could be moving to the left and speeding up. Okay, we're interested in the situation where it's moving to the right and slowing down. Eventually we want it to come to rest. So let's suppose it comes to rest here. So we want to find the distance that it travels in coming to rest. Notice that we are not dealing with uniform acceleration. The acceleration vector is going to change as the particle moves from here to here. The speed of the particle is actually going to change, as we'll see. And the acceleration varies with the speed. Notice in this case, of course, that if we want to find the acceleration at a particular time, we cannot use this formula, because this formula does not give us the acceleration as a function of time. It gives us the acceleration as a function of v. So to find the acceleration when the particle is here, we have to know what v is when the particle is here and plug into this thing to get the acceleration. Now we know that the acceleration is the rate of change of velocity with respect to time, dv dt. However, we are not looking for v as a function of time. We're interested in the distance s travelled before the particle comes to rest. When the particle comes to rest, the speed v is going to be 0. So we want a formula connecting v and s. So it's best not to separate the variables with this equation and get v as a function of time. It would be better to change this derivative into something involving v and s. Now we saw how to do that in a previous video. We saw an example of how to turn dv dt into a derivative involving the variable s. What we do is we write ds underneath here and compensate, of course, by putting ds on top. Well, I put the ds over here maybe. So multiply dv dt above and below by ds, and then you get ds over dt times dv ds. Now the t is still here, but what is ds dt? ds dt is none other than v, the rate of change of distance travelled with respect to time. Distance over time is speed. So we can replace dv dt with v times dv ds. Now we can separate the variables and try to get v not as a function of time, but as a function of s, distance. Because we're after distance here, we will be setting v equal to 0, and we will be solving to get s, the distance travelled when v is 0, when the particle comes to rest. Okay, so we bring all the v's to one side, so we just need to divide both sides by the right hand side, minus v squared over 400 plus 16. And we must get rid of the ds here on the left hand side, so we need to multiply both sides by ds to get rid of the s. Now the v's are on the left and s's are on the right. Now, notice we have v squared in the denominator and we have v in the numerator, v to the power 1. We have seen examples like this in previous videos. V squared plus some quantity. If we differentiate this, with respect to v. Well, if we differentiate ln of something, we get 1 over that argument, whatever it is, v squared plus whatever, and we multiply by the derivative of the argument of ln, so we get 2v. Alright, so we have v squared underneath and we have v on top. That's exactly the situation we have here, but you know, we need to get this thing into the form of examples that we saw in previous videos. So we don't want v squared over 400, we just want v squared. So we need to multiply above and below here by minus 400. And if we multiply below by minus 400, we get a plus v squared, and we have minus 400 by plus 16, that's minus 6400. Okay, so we want to integrate this thing, and on the right hand side we want to integrate ds. Now we can solve this problem using indefinite integrals, that is integrals without limits. You know, we'll integrate this thing and we'll have a constant of integration from both sides, and we bring the constant of integration to the right hand side to get plus c, and we try to find out what the constant of integration is, and then we get a particular solution. V is a function of s. Then we can continue to solve the problem. That's if we have indefinite integrals. But we can turn this into a definite integral problem by looking at limits, putting limits on it using the boundary condition, which says that when s is naught, the distance from the starting point is naught, then v is 40. Okay, s is the position of the particle from this origin here, so when the particle starts here, s is naught, and the initial speed, the speed at time 0, or the speed when s is 0, is 40. So when the distance is 0, the speed is 40, so that's the lower limit. So we are interested in the upper limit here. That's the distance the particle has travelled when it comes to rest, when the final speed is 0. Now let's do the integration. We take minus 400 out, ln of the denominator. But we need to compensate, because if we differentiate this, we get 1 over v squared minus 6400, and we multiply by the derivative of what's inside the bracket, which is 2v. So we'll get a 2v, so we need to put a 2 down here. So we've seen examples like this before. Okay, if you differentiate this by the chain rule, you know, let's just go through it. If we differentiate ln of v squared minus 6400 with respect to v, well, you get 1 over the argument of the ln function. But by the chain rule, we must multiply by the derivative of the argument of the ln function, which is 2v. Differentiate v squared to get 2v. So you see, we get this factor of 2, so to compensate we stick a half here. So we'll have a half here. So we'll just get v over v squared minus 6400. That's what we want, v over v squared minus 6400. The minus 400 is just left out here to one side. So we need this factor of a half. So I have it here. Of course, the other way to do this is to use substitution method. Let u equal this thing and calculate du dv, replace the dv, and so on, and you get an integral involving u. You can do it that way too. Of course, all of this only works because we have v to the power of 1 on top. If we had, say, v squared on top or v cubed, then we couldn't use this approach. Okay, so that's the left hand side. On the right hand side, we're integrating 1 with respect to s. Well, that's just going to give us s. We plug in the upper limit, which is s, plug in the lower limit, which is 0. So we get s minus 0, which is s. Of course, we have limits on this thing. Nearly forgot about these. This runs from a lower limit of v equals 40 to an upper limit of 0. Now, what you could write for this upper limit is s of 0 if you want. Okay, because we're getting distance s as a function of v. So what's inside here is not t, but v. So this is when, so we're getting s, the distance when v is 0. Okay? So that's what's inside the bracket there. S at v equals 0. Plus sign here. Okay, so we've minus 200 ln of 0 squared plus 6400. Minus sign, and we write this thing down again. Minus 200 ln of 40 squared plus 6400. That's 1600 plus 6400, which is 8000. Okay, if you want to, you can factorize out the 200 and write this as 200 times ln of 8000 minus ln of 6400. Well, ln of 8000 minus ln of 6400 is ln of 8000 divided by 6400. Okay, that's from ln A minus ln B is ln A over B. Simplify this down to get ln of 5/4. To 2 decimal places you get 44.63 meters. In part 2 we want the average speed of the particle during the motion. So to get the average speed of something, we get the distance travelled by it and divide by the time taken. So we have the distance travelled, and now we want the time taken for the particle to go from here to the point where it comes to rest. So when the speed is 0, we want to find out what the time is. That's the time taken. So we want a formula connecting v with t, and that comes from this differential equation here. So we go back to this and we leave dv dt as it is. That's the acceleration. So we separate the variables v's to one side, t's to the other side. Now I'll multiply this thing above and below by minus 400. Alright, so the v squared will appear on its own in the denominator. So we've so we're going to get plus 6400 here. Okay, so we 400 times v squared over 400, that's v squared, and 400 times 16 is 6400. And they've taken the minus sign out here. Alright, so this is equal to dt. We have to integrate both sides. So the minus 400 is just a constant. Now, we've seen integrals. Well, actually, we haven't seen integrals of this type before. So let's just see what form it has. See, the type we saw before was a type with v on top, v to the power of 1. And we could use ln of the denominator, because the derivative of the denominator was a constant multiple of the numerator. The derivative of the denominator is 2v, and 2v is twice the numerator. Okay, that was the situation before, but now that v does not appear on top, so we can't use a substitution method. But if you go to tables, you'll see that this is one of the standard integrals. It might be written like this in your tables. Okay, this has got the same form, just replace x with v. A is a constant, so a squared here is 6400, so you can see straight away that a must be 80. 80 squared is 6400. So I have a table of integrals here. We're looking something 1 over the form of the form 1 over x squared plus a squared. So here it is, 1 over a inverse tan x over a. So as I've said already, here's our a squared. So a is the square root of 6400, which is 80. So we're integrating 1 over v squared plus 80 squared. So that's going to give us 1 over a, which is 80. Inverse tan x, well, the variable is not x here, it's v. And the constant a is 80. Okay, we can solve this using definite integrals. I was going to do it using indefinite integrals and get our constant of integration, but I'm going to put limits on these to turn them into definite integrals. So the initial time for the problem is 0. And the final time is what we're after. This is the time when the speed is 0. So t is a function of v. Okay, so what's inside the bracket is 0, because the upper limit here is 0. The particle starts off with an initial speed of 40, and it slows down, and eventually it comes to rest, so its final speed is 0. So if you like, the lower limit here is the time when the speed is 40. If we get t as a function of v, and that time, as we know, is 0. Okay, that's the initial time. So if we go back up here, at t equals 0, the speed is 40, and we want a time when the speed is 0. So the limits on the left hand integral are from 40 to 0. Now let's integrate dt. Well, that's integrating 1 with respect to time. That just gives us t. And the limits are from 0 to, well, what we're looking for. We can call it t prime or something. We should really use a different notation for a limit than we do for this variable. But usually it's understood what we're trying to do. So we can just leave it like this. Put in the upper limit t, and then you have minus 0. Well, t minus 0 is just t. Well, if we just put in this, actually, we'll have the time when the speed is 0. So simplifying a bit here, we get minus 5. Okay, so we plug 0 in for v, so we get minus 5 inverse tan of 0. Then we have minus sign. Copy this out again. Minus 5 inverse tan 40 over 80, which is a half. Okay, so this works out to 5 inverse tan of 0 is 0, so we get plus 5 inverse tan of a half. Make sure your calculator is in radian mode. So the time when v is 0 is 2.32 seconds.